So welcome to this lecture on discrete probability distributions. In the previous session we had seen the general properties of random variables. Now let us specifically get into well-known probability distributions. Probability distributions are basically divided into discrete and continuous, and among the discrete probability distributions we can specifically mention binomial, Poisson, geometric, and hypergeometric. So these are generally some of the distributions that can be connected to practical situations. We will specifically discuss the binomial and Poisson probability distributions. So when you look at a binomial distribution, we say a random variable x follows a binomial distribution with parameters n and p. X is the number of favorable outcomes. So n stands for the number of trials, p stands for the probability of success per trial. X is the total number of successes out of n trials. So we say x follows the binomial distribution with parameters n and p if x has the mass function f of x is equal to ncx p power x q power n minus x, where x takes values from 0 to n. Now the design of this mass function is very simple. ncx stands for the number of combinations of getting x successes out of n trials. And because we are having p successes, therefore q is the probability of failure, p is the probability of success. So x successes is estimated by p power x and n minus x failures is covered by q power n minus x. Because the trials are all independent, therefore the mass function can be easily designed like this. Now there are some limitations of the binomial distribution. One of the serious limitations is that n should not be very large. The number of trials that you conduct should not be too large. So we say favorable conditions to apply binomial distribution. One of the conditions is n should not be large. We still have to specify what is large and what is not large. Specifically, n should not exceed 30. So n should be less than 30. And 2, probability of success per trial should not be low. Under these conditions, the binomial approximations are very accurate. Suppose these conditions are violated, that is, when n becomes too large or p becomes too small, then we are actually driving the binomial distribution towards the Poisson distribution, which we'll discuss a little bit later. So what are all the basic information that we can derive out of the binomial distribution? So let's write a few properties here. The mean of a binomially distributed random variable is n into p. A slightly longish derivation exists about which we need not bother. N into p. So if we just multiply the binomial parameters, you get the mean. 2. The variance of the binomial distribution is NP cube. These are well-known established results. But there is a slightly important property about the mode or modes of a binomial distribution. There are two cases when n plus 1 into p is not an integer. Probability of x is equal to r will be a maximum if r is equal to the greatest integer not exceeding n plus 1 into p. Please understand this notation. This is the greatest integer not exceeding n plus 1 into p. And the second case, n plus 1 into p is an integer. Here it is not an integer. Then probability x is equal to r will be a maximum for r is equal to m minus 1 or m, where m is n plus 1 into p. So these are well-known theoretical results that one must remember. I think I should once again explain the modes very clearly. When you have the quantity n plus 1 into p not an integer, the binomial distribution will have exactly one mode. And that mode occurs when r is equal to the greatest integer estimated through n plus 1 into p. For example, n plus 1 into p is 5.7. Then you take that as 5. Okay. When n plus 1 into p is an integer, then the probability will be a maximum when r is equal to m minus 1 or m, where m is equal to n plus 1 into p. So these things may be remembered as very important results. And as I told you, if you violate the conditions of the binomial distribution, that is if you enlarge n very high to a very high level and p very small, then you are driving the binomial distribution toward Poisson. So let's now take up a few problems on the binomial distribution and see how these properties can be exploited to do some numerical problems.